In this class, we will see in detail about the translation operators. That is, first we will see the definition of unitary operator. Then we will see the spatial translation operator, and then we will see the momentum translation operator in detail. Before dealing with the translation operator, we will see the definition of the unitary operator. As I have given few lecture on unitary operator, here I am going to give only the definition of the unitary operator. A linear operator U is said to be the linear unitary operator if its inverse is equal to its Hermitian conjugate. That is, U dagger is equal to U inverse. You know the meaning of U dagger. If U is the unitary operator, then U dagger is Hermitian conjugate, and U inverse is inverse of the operator. Now you multiply by unitary operator on both side on right hand side, because the order of the operator is important in quantum mechanics. First you multiply by u in the right side of this expression. So u dagger u will become u inverse u. I am multiplying by both by the right hand side, which is equal to 1 unit operator, not unit operator. In similar manner, if you multiply the above expression by u in the left hand side, that is u dagger will become u inverse, which is equal to 1. This is the definition of the uh, unitary operator. The one of the very important property is it preserves the norm. That is by uh, by carrying out this unitary operator, nothing will change. Particularly, the physical property of the wave function will not change. That is the very important uh, point to remember. First, we will see the spatial translation. The spatial translation t, which is a function of alpha, is equal to e power I alpha p over h cross. So this is the spatial translation operator. Here, the important thing to be noted is, see, for spatial translation, we are using the momentum. So both are canonical conjugate. Now, this P over H cross, this P over H cross is called generator. So, here now the you know that T uh, T dagger T is equal to e power, because we are taking complex conjugate, it is e power I alpha p over h cross multiplied by e power minus I alpha p over h cross, which is equal to 1. If you multiply both, you will get 1. Uh, as I said, this P over H is generator. That is, this is momentum generator for facial transition. Facial translation. Momentum operator by definition is equal to, in quantum mechanics, it is H cross K over H. Here we have already H cross. So P is H cross K, and here already we have H cross will get cancelled, so you will get only K. The generator is P over H cross. Now let us see, P over H cross is equal to K, which is equal to 2 pi by lambda. So naturally, this is having generator is having the dimension of inverse of length inverse. So naturally, this alpha will be alpha has a dimension of length, so that in the argument, exponential argument must be a dimensionless quantity. So we know from this alpha must be having the dimension of length. Now we will see the commutation relation. That is commutation of x with translation operator t of alpha, which is equal to x commutation of x with e power minus I alpha p over h cross. We know from the commutation relation that this commutation of A with function of P is equal to the commutation of A with P multiplied by the derivative of P, that is F prime P. You apply this rule to the above commutation relation. Here A is equal to X and F of P is equal to T alpha. Here alpha T alpha is function of P. So you apply this rule here uh, in the above commutation relation, then you will get, that is x commutation of x with T alpha, which is equal to x commutation of x with P, then derivative of this exponential term, which is equal to minus I alpha over h cross e power minus I alpha p over h cross. That is a, here p is the momentum function of p. Here see the this commutation is equal to a commutation of a with the function of p is equal to commutation of a with p. Here p is a momentum, and the derivative of that function, that is a derivative of this exponential term, which is equal to minus I alpha over h cross uh, e power minus I alpha p over h cross. Now it is well known fact that commutation of x with p is equal to I h cross, and this exponential term is T alpha, that is a translation operator T alpha. This is T alpha. Now you substitute this, then you will get that is x uh, x commutation of x with T alpha is equal to this I h cross and this derivative minus I alpha over h cross T alpha. Now here this h bar will cancel with this denominator h bar. Then this and this minus I into minus I is equal to 1. So if you multiply both the term, you will get only alpha, and multiplied by T alpha. That is, this commutation of x with T alpha is equal to alpha times T alpha, because here only the term left is alpha. So alpha times T alpha. So we have seen that the commutation of x with t is equal to alpha times t. If you expand this commutation relation, then you will get x t, which is a function of alpha, minus t, which is a function of alpha x, is equal to alpha times t, which is a function of alpha. Now what I am going to do is you bring this to right hand side. You bring this term to the right hand side. Then what you will get is uh, x x t alpha is equal to, here x is an operator, alpha t alpha plus the t alpha x. So you are not supposed to change the order of the operator here. Now what we are going to do is let this operator act on the get x, that is get x on both sides, that is x t alpha uh, when act on x, which is equal to alpha t act on get x. Similarly, t alpha x act on uh, here x is an operator get x. So when x act and operator x act on get vector x, you will get x. Here x is a number. Here x is an operator. What I have shown in red color bond is a number. Is an here x is an operator. So you will get x get x. Now, since it's a number, you can bring this to the left side of the operator t. Then this can be written as x plus alpha. That is, I can explain this here. That is uh, t alpha I can get x. Now I am taking x first term, sorry, second term first x, and this is plus alpha. Port in port term I have t. Since I have taken this x left side of the operator t, I can because it's a number, I can take this x plus here alpha also is a number. X plus alpha is equal to t alpha x, t alpha get x. Now, one important point is that is here uh, x is an eigenvalue of operator x. Naturally, then that is I can simply say that get x is uh, eigenvector of operator x. Then t x get x also the eigen vector of the operators x. But however, here eigenvalue is x. Here eigenvalue is x plus alpha. So translational operator moves the x from x plus alpha, where alpha is uh, number. So there is a shift. Uh, in this case, x shift from x is equal to 0 to x is equal to alpha. There is a shift in the position. Once you translational operator act on the get x, it will shift by a distance alpha. So that is the importance of translation operator, that is t alpha. So far we have seen the position translation. Now we are going to see about the momentum translation. And the translation operator for momentum is t, which is a function of beta, is equal to e power I uh, beta times x over h cross. Uh, so this is nothing but you can you remember that it is based on the Fourier transformation. So here you will get plus instead of minus. In the case of partial translation, it is minus. Now it is plus I beta x h cross. And another important thing is this t dagger t is equal to this e power minus I beta x, because it's a dagger. If you take dagger, you will get minus, and d beta is equal to e power plus beta x over h cross, which is equal to 1. So this translation operator is an unitary operator, you know. Here the generator is x by h cross. Previous case for partial translation, this translation generating operator is momentum based one. Here generating operator is position. So both are canonically conjugated. That is very important point. Then what is the dimension of beta? uh, because the argument of exponential must be dimensionless quantity. So, as we have seen in the previous case, is it must have beta must have dimension of momentum, so that we can add this beta with the momentum. So this will have dimension of momentum. So previous condition is equally applied here also. So this is the momentum translation operator. For momentum translation operator, we will see that the commutation of momentum with the translation operator dp beta. That is here instead of x we are using p, because this momentum translation based on the position operator. So this is equal to P computation of P with this translation operator, which is position basis e power plus I beta x over h cross. Here also use that same relation, using the relation that just we have seen for position translation. The commutation of A with the function of P is equal to commutation of A with P multiplied by the derivative of function P. So apply it in the above equation. Then we will get that the computation of position with the translation operator t is equal to p e power I beta x h cross. Here the function is this exponential term. P is equal to x. So the computation of p with the x, I am using the same procedure applied for position translation. So this is equal to p commutation of p with the x and the derivative of this exponential term. Derivative of this exponential term is I beta over h cross, then that exponential term. Here commutation of p with the x is minus I h cross. Previous case it is x commutation of x with p, which is plus I h cross. Here it is minus I h cross. Now you can say this the commutation of p with translation operator is this minus I h cross I beta over h cross and this exponential term. Here applying the same rule, if you multiply this green color parameter, both the parameter, h cross will cancel each other, then minus I into I, that is I minus I squared is 1, so this will become beta, and this exponential term is naturally the t. So this will become t beta. uh, so now this commutation is that is p commutation of p with t is equal to beta time t beta. So now we will see the uh, commutation relation of p with t, which is equal to, just now we have seen, beta times t. Now you expand this commutation relation on left hand side, which is equal to p t minus tp, which is equal to beta times t. Uh, Now what we are going to do is you bring this second term, that is this second term, to the right hand side. You bring this second term to the right hand side. You bring this to right hand side. And then what you will get is you will get PAT, which is equal to PAT beta times T plus this second term will become plus T, which is a function of beta times the operator P. So T and P are operators, so we are not supposed to change the order. Now let this operator act on the position, momentum vector P, momentum vector P on both sides. So this get P. Uh, so momentum, this operator act on the momentum get vector P. Then this second term, you can see that when the operator P act on the get P, then it will gives you the eigenvalue P and this get P. Since eigenvalue is a number you can bring to the left of the operator, then you can take that as common, as I have given here. Right hand side I am keeping as it is. uh, then in the left hand side, this P plus beta, second term contain P, the first term is beta. Both are numbers, so I am taking left side of the operator. So this operator act on the get P. Since the get vector P is an eigenvector of operator P. Naturally, here T get vector T, when T act on the get vector P, also the eigen, that is this is eigenvector of operator P. This is the eigenvector of the operator P. Of course, here the eigenvalue is P. Here this eigenvalue is, in this case, P plus beta. Now, when translation operator act on the get vector P, then the position of the vector changes by an amount beta. That is, P will go to P plus beta. If it is plus, it is plus beta. If it is beta, may be plus positive axis or negative axis. So this is about the position and momentum translation operator. Thank you very much for watching my video and supporting me continuously.